CPU Part 1. In this nugget, we talk about CPUs, and this will be Part 1, where I'll start off with a conceptual description of the CPU. And although I don't think you need to memorize most of that for A+ exam objectives, it will be important to understand conceptually how the processor works and the flow of the data through the processor in order to help you be a good A+ technician. Then we'll also talk about CPU characteristics, such as whether or not you're going to use a multi-core processor, what kind of cache, what levels of different cache the processor has, and the like. Isn't it amazing what processors can do these days? I mean, they have millions and millions of circuits on a tiny little, normally a square little packaging, and they're able to do so many things at once, far more than the human mind is probably capable of doing at any one time. For example, not long ago, I went to my daughter's cheerleading competition. It was the state cheerleading championships, and there's hundreds of cheerleaders all around, and it was kind of chaotic. But I decided to take a little break, and I decided to go to the men's room. And as I was on my way there, I thought of calling my son, who was at home and had no interest in cheerleading whatsoever. So I thought I'd call on him and see how he was doing. Well, I could only think of one thing at a time, so as I'm talking to him on the phone and walking into the men's room, it was suddenly then that I realized I hadn't walked into the men's room at all. I'd walked into the ladies' room, and yes, there were all kinds of cheerleaders in there, and they were quite alarmed to see this fella walk into the ladies' room. Anyway, I'd like to point out that right now that those high kicks that they can do, those are not just for show. I think they're like some ninja cheerleading moves that they can do. Anyway, enough about that. The problem there was, of course, I could not seem to think of two things at once. I couldn't talk on the phone with my son and at the same time pay any attention to where I was going. So if I had been able to multi-process a little bit better, I probably would have avoided a little bit of trouble and a concussion. Well, as we take a look at a kind of a logical diagram of a processor, we can kind of see how it's going to be able to do many different things at once. First of all, the speed at which it's able to calculate a lot of the different things that we'll look at is just staggering in and of itself. But there's also the fact that it has two arithmetic logic units. I'll come back to that here in a little while. But basic idea there is that's what really does the thinking on the processor. Almost everything that takes place in a processor boils down to binary types of data. Now, when you think of binary data, what we're really working with there is zeros and ones. A zero might be off or false, or it could be combined with other data like other zeros and ones to mean something else. A one might be on or true, or it could again also be combined with other zeros and ones to combine to add up to other kinds of data. For example, zeros and ones eventually make up things like an IP address, which is how you're identified on the network, or how your computer's identified on the network, and so forth. Anyway, all of those zeros and ones have to go in and out of the processor somehow, and the way they do that is through this little bus that we see right here. And this bus here actually has a number of different names that I've listed right here. One is the data I/O bus. It's one way of describing it. A lot of people call it the front side bus or the FSB. That's probably the one that I would focus on the most, or that I think is most frequently used. Then there's the external data bus, and then there's sometimes called also the CPU bus. But they're all generally the same thing. There are some minor distinctions between the emphasis on some of them, but overall, they're the interface that goes on between the processor itself and all the logic the processor is able to do up here, and the memory. Actually, it's this bus right here is where it transmits data from the processor to the main memory. And if you want to put that down here at the other end of the arrow, that's one way to think about that. Now, another characteristic of this bus is that it's between 4 and 64 bits wide. Just depends upon the generation of processor and the vendor of processor. Now, you're probably thinking, okay, probably when this things first got started, it's probably 4, and then maybe, who knows, maybe it went to 8 and 16 and 32, and nowadays we're 64 bits wide. Well, that's not actually completely true. You see, it would seem to make sense to make this as wide as possible, and for a while, it did get to 64 bits wide. And that's kind of like having a 64-lane highway, or a horse race with 64 different gates and 64 different horses charging out of the lanes at the same time. But in reality, it became difficult to synchronize the data from all those different lanes all at once. So what they found out that they could do was that actually turns out that a lot of the current processors right now are actually about 4 bits wide, And those are the fastest processors because they actually send their data serially along those lanes, and they're able to send data faster on 4 lanes of traffic than they are on 64. Think of it another way. If you had 64 lanes of traffic, and maybe you had cars in each one of those lanes, each one of them going 55 miles an hour. Let's just do some math here real quick. Okay, so if I had 64 lanes, and each one of them was going 55 miles an hour, that would add an aggregate speed of 3,520. But if I have 4 lanes, where's the clear on this thing? I'll just use the escape key. Okay, if I have 4 lanes, and they're all going at 1,000 miles per hour, then we have 4,000 aggregate, don't we? 4,000 miles per hour aggregate. So, even though it's fewer lanes, because of the speed you can send through each one of those lanes, it's actually going to be better. Now, by the way, all this stuff that I'm telling you about here, most of this really is going to be a little bit academic. You don't have to know a lot of this for the A+ exam purposes, but the reason why I tell it to you is because it will help you to understand some of the other characteristics about processors that you'll need to know later on. For example, you do need to know what the front side bus is, and that it's the CPU's interface to the main memory on the motherboard. Okay, so keep that in mind. And then as we move up the diagram here, let's also take a look at this control unit. This just handles exactly what you would think. It controls the functions that go on between all the functions going on in the processing of what takes place in the CPU and going out through the front side bus down through here. Okay, just kind of is the traffic cop for all of this stuff that goes on. Now then, the arithmetic logical units, or ALUs, they're responsible for the calculations. Really, a processor mostly just performs mathematical calculations because all the numbers come in, again, as zeros and ones and so forth, and everything eventually has to be calculated somehow. Well, the power of the processor is in the arithmetic logic units. Also, by the way, this is a single processor diagram. If you have multi-core processors that have 2, 3, or 4 processors, for example, you can take most of this diagram, at least on the top part of this, and multiply that times 2, for example, for a processor that has 2 cores, for example, or times 4 for one that has 4 cores. Then we also have something here called the internal data bus, or the IDB. This handles all of the exchange of data between the registers and between the arithmetic logic units, and kind of the ping pong ball that goes all back and forth between all of this stuff. Kind of making you dizzy there, aren't I? Okay, follow the ball, okay? Anyway, this internal data bus is where we identify whether or not we have a 32-bit processor or a 64-bit processor. That's where the true test is of whether it's 64 or 32. Now, if you're currently buying new computers and new computer equipment, you're going to find out that I'm not even sure if you can buy a 32-bit processor anymore, unless it's like from a garage sale or something. It seems like anything new that you buy right now is going to be 64 bits wide. However, many of your customers, which are bringing computers to you that are potentially years old, will probably still be 32 bits wide, and I would venture to say that many of them are also running 32-bit operating systems and software. Now, as a quick tangent here to this as well, if I have a 32-bit processor, let me just give some scratch space down here, 32-bit processor, then I can only run a 32-bit OS. Okay, that's it. If I have a 64-bit processor, then I can run a 32 or a 64-bit OS. Okay, because the way the instructions are up in here, the processors are capable of still understanding the 32-bit language. So, in fact, when the 64-bit processors first came out, even though they were 64-bit processors and everybody was all excited about how potentially powerful they were, well, the operating systems that were installed on those new computers from vendors were still usually 32-bit versions of Windows XP or 32-bit versions of Windows Vista. In fact, to my left right now, I am upgrading a computer that's a Windows Vista computer. It's got a 64-bit AMD processor, but it was installed from Dell with a 32-bit operating system. So thank you very little, Dell. I have had the same thing happen from many other manufacturers. They put a big sticker on the cover of this laptop. I'm looking at it right now. It says AMD 64 Athlon times 2, and everyone's all excited, and they're going to get this 64-bit processing power. Well, that never happened. They only stick with the 32-bit operating system that they install. Now, a lot of the newer ones, this laptop I'm looking at is probably a year and a half old. A lot of the stuff that's come out in the past year really is either 32 or 64-bit, and so they're doing much better about that. Kind of one rule of thumb is, if you go to the computer store and you look at laptops or desktop systems, if it has 4 gigabytes or more of memory, almost always you're going to find that it also has a 64-bit processor and OS. Oh, and I guess I better explain what these registers are too, huh? A register is kind of like a scratch paper. So when it does these calculations in the ALU, sometimes it has to have a holding place to kind of put something down while it thinks about something else, that kind of thing. Put another way, it's like, oh, well, like when my son comes home with homework at math. He's actually pretty good at math. He's a very smart kid. But strangely, he did not inherit that math capability from me. I don't know where that came from. So anyway, when he says he needs help with certain homework, I'll have to try to help him figure that out. But I've always got to write it out on scratch paper, whereas some people can figure this stuff out in their heads. So we'll say, 8 divided into, I don't know, 64. What is that, Dad? Let me think. Oh, that is 8. Okay, so I can figure that out, but I have to kind of write it down. Well, that's kind of what the register is there to it. Figures all that stuff out, or at least it's kind of a holding area for some of the calculations in the ALU. Now, you may have also heard of another term related to processors, something called hyperthreading. Okay, I'll just put HT here for hyperthreading. And what that's about is the ability for the processor, and again, even though we have two sides of this right here, this diagram represents a single processor, a single core processor. We'll talk more about dual core, quad core, any kind of multi-core later on. But with hyperthreading, it will appear to the operating system as if it has 2 processors in it. You see, what happens is each one of these arithmetic logic units is able to handle data independently and able to accept threads on its own. And so as a result of that, the processor will think that it's actually got 2 processors in it. Okay, so for example, and this doesn't really work out anymore because I have a quad-core processor. But if this was a dual-core processor, if I were to open up Windows Task Manager, which you can get to by right-clicking on the task bar and choosing Start Task Manager, or I usually just hold down Control-Shift-Escape, and that usually opens this up as well. Anyway, with hyperthreading, even if I had a single-core processor, it would still show 2 of these. And this is a representation of hyperthreading is how that would be. And again, in this case, I'm not really using a processor that uses hyperthreading because I have 4 cores inside of this instead, which is pretty much the same as 4 separate processors. And then over here on the left-hand side, we have something called the backside bus, which is primarily the interface between this whole cache system that we see over here and the rest of the processor over here on the right. You see, what happens is a lot of the data that is processed in and out of a system is going to be repetitious. It's going to be the same data over and over again, or the same instruction set that goes in and out over and over again. So what happens here is the processor has to be able to retrieve that data from somewhere. In the worst case scenario, it might have to retrieve it from the hard drive, which is dramatically slower than anything on the processor. So the other alternative there would be to pull it out of something like one of the caches. You see, if it's already accessed the data at one time in the past, then it might still be cached, because it will identify, it kind of has an intelligence where it can identify frequently used data, and then if it looks like something's used a lot, then it will just store it in one of these caches. Now the L1 cache, these are all logically the same size in the diagram, but the L1 cache is usually much smaller than the level 2 or level 3 cache. However, the level 1 is fastest. So up at the top is the fastest, but at the bottom of this is the largest. I'll put F for fastest. Okay, and L for largest. Okay, so we have this very fast right here. Now, the level 1 cache interfaces at the same speed as the processor itself here. So this is an extremely fast backside bus function that goes on between the arithmetic logic units, or the processor itself, and the level 1 cache. The level 1 cache is also in chips on the actual processor die, as is the level 2. Now, level 2 is a separate cache, and why don't we just make the level 1 bigger instead of having a separate level 1 and level 2? Well, the level 2 cache is usually made with a little less expensive manufacturing process. As a result, it can also be larger. Okay, it just has to do with some form factor issues and things like this and some processing issues. There may also be a level 3 cache, which is going to be even larger. Level 3 initially, in a lot of systems, started actually off die. It was actually out here somewhere. I just kind of ran off the edge of my little drawing pad here. But anyway, it initially started off out here, and it was still pretty fast, but nowhere near as fast as level 1 and level 2 cache. But most of that's been moved onto the die right now. Now, another thing to consider here is that a lot of times the level 1 and level 2 cache kind of nowadays get mashed together, and I just kind of represented that out here as the advanced transfer cache. That's another way to refer that. Sometimes it's just called the ATC, and it's kind of a glob of memory now that is our cache. And then this cache out here just represents all of this kind of logically all together. Anyway, the key things I think you want to remember for that is that level 1 is faster than level 2, level 2 is faster than level 3, level 3 is the biggest. I don't know why there's an H there. I just realized I have an H there. That's not supposed to be there, folks. Scratch that out. But level 3 is the biggest, but it's also the slowest of the caches. However, even level 3, much faster than main memory, much faster to access also than retrieving data off of the hard drive. And then the other thing I would keep in mind for sure is that the level 1 cache, at least, operates at the same speed as the processor itself, and so it's definitely a performance advantage if you can get a larger level 1 cache. All consumer-level PCs and laptops these days do have some caching. However, a lot of servers will have larger caches and will be able to perform much faster, but of course at the expense of a more expensive processor. Now let's also take a look at some other characteristics of the CPU. One of those would be the core speed. For example, if I go back to my initial diagram that we started with here, how fast is this processor? Well, let's just say it's a I can't seem to write here, 3.2 gigahertz processor. That's 3.2, that's over 3 billion actually, 3 billion cycles per second that this processor is capable of operating on. By the way, to give a sense of scale there, 3.2 billion cycles, that's more times than the human heart beats in a lifetime. And that all takes place in 1 second, 3.2 gigahertz here. So that's extremely fast. Anyway, this is also going to work on a multiple of the front-side bus speed. So let's say my front-side bus speed was 800 megahertz. Well, we would have to divide 800 megahertz into 3.2 gigahertz. Now, some of the things that I talked to you about on that diagram earlier really relate to a lot of the CPU characteristics. One of the things I didn't address too much, though, is the core speed. So if I go back to that diagram, you might go to the computer store and you might order a processor. Well, how fast is it? Is it 2.3, 2.4? Is it 3.2 gigahertz? How fast is that? Well, let's say, for example, it's 3.2 gigahertz, which is pretty fast. That's over 3 billion cycles per second that this processor is capable of running on. Now, to put that in scale a little bit, the human heart beats less than that in a lifetime. Okay, so this in 1 second is able to perform more operations or more cycles per second than the human heart beats in a lifetime. Wow, that's huge. Now, another thing to think about, though, is that remember our external data bus or our front side bus here, this interfaces with a clock cycle on the motherboard that who knows how fast that is. Let's just say it's 800 megahertz. Sometimes they're 1066 megahertz. You know, so different speeds there. The performance that you can get out of the processor is going to have to be usually a multiple of this. For example, you know, 8 goes into 32 4 times. So there might be a 4x multiplier or something like that that allows that to happen. And that's kind of moves over into another topic, which is called overclocking. Now, even if you do not implement overclocking to kind of squeeze a little bit more performance out of your processor than it might otherwise give you, most motherboards will interface with the processor at some multiple of their front side bus. And just out of the box, you know, default settings, you haven't done anything fancy. It might still be a multiple of, you know, like 4 or something like that. So anyway, that's one of the things to think about there is the core speed. It will have to, again, interface with the front side bus at a certain speed in megahertz. So again, if my core speed is 3.2, I can't write, 3.2 gigahertz, and my speed in the megahertz there is 800, then again, I might have to have a multiple of 4 or something like that. Yeah, and for a little clarity, let's do that here as well. So if I convert this to megahertz, let's do this to megahertz as well. So if I convert 3.2 gigahertz to megahertz, that would be what? 3,200 megahertz divided by 800 would be 4 even, right? Yeah, 4 even. So that'd be 3200. Yeah. So that would be, I would be using a multiplier of 4 on the motherboard. I probably could configure that through some utility that I might have, depending if my motherboard supplies that for overclockers, or I'd have to go into the BIOS normally to be able to configure that at 4. Or if I wanted to kick that up to 6, now I'd be overclocking, right? See, what would that give me? So 6 times 800, that would be 4.8 gigahertz, wouldn't it? Now, that would also make my processor extremely hot. We'll talk about cooling a little bit later on. That might be kicking it too much, but a lot of the times you can go 4.5 or 5 or something like that. If you went 5, that would be, of course, 4 gigahertz. So you can see that that might be a little bit more reasonable. The higher you go, by the way, the more you overclock, the less stable the system could possibly be. There's also that data path that we talked about earlier, the bit width. Remember, it can go up to 64, but very often it's really going to only be like 4 nowadays with a lot of the current processors because they're so fast. We talked about cache as well. Level 1, it might only be 512 megabytes or maybe a megabyte. Level 2 is going to be usually larger. Maybe it's 2 megabytes, and level 3 might even be more. Maybe you got 4 megabytes. Then there's the advanced transfer cache, which kind of mashes some of this together. For consumer level PCs, these will start off small and go larger. For servers, they might start off a little bit larger. It might be 2 megabytes here or 4 and then go larger. Okay. Also with multi-processing, this is where I would have multiple processors actually on the motherboard. We don't really see that much in consumer level PCs. And as an example of that, I have a photograph here of an old server that I've still got around. And as I zoom in on this, you'll see that it's got one processor in it. It's kind of dark there, but that's actually a heat sink, a really large heat sink. It's got to be, 6 inches tall, and it sits off the motherboard there. It's got cooling fins all over. It's made of aluminum. It's got some copper tubing in it as well, which all helps to cool it down. And it's got this green cooling shroud that covers the top of it. On the other side of this, it's out of vision right now, out of view, but there's an intake fan that pushes cold air in over the top of this heat sink right here. Anyway, this heat sink right here, the first position would be known as CPU 0 because it uses ordinal numbering. Now, over here in position CPU 1, and by the way, I would remember how these are numbered, okay, because it starts at 0 in ordinal numbering, which means that it doesn't start with 1, it starts with 0. So CPU 0 and CPU 1. Anyway, in CPU 1, notice that I don't have any processor here. I just have the socket itself. But this server motherboard is capable of multiple physical processors. Now, we don't really see that too much anymore on desktop computers or even high-end workstations because of multi-core technologies, but a lot of servers will have room for 2 or 4 or 8. Some of them can even go up to 64 or more processors on a single computer. Now, in order to get to that level of processors, they have to use something like Windows Server 2008 Data Center Edition. They have to do some other things. Of course, you're not going to put all of those processors on one motherboard. They're kind of chained together through a number of different racks and things like that. But anyway, that's beyond our scope for A+ exam objectives, but I just wanted to share that much with you anyway, that you can, a lot of times with servers, install multiple processors there in multi-processing implementations. Also, the operating system has to support that. For example, the old Windows 95 and Windows 98, well, they didn't support multi-processors at all, so it wouldn't matter if you installed multiple ones. However, current operating systems, all current operating systems that you would work with and that are part of the A+ exam do support multi-processing. Now, if it supports multi-processing, it'll also support multi-core, and this is what we're going to more likely see on consumer-level PCs, and the reason for that is because if we take a look at something like this is the CPU that I'm actually recording right now. The sound of my voice as I record is traveling through this CPU somehow or another and being all broken up into zeros and ones or something and spit out the other side probably, and then it's being sent to the hard drive. Anyway, this CPU right here is a quad core, so it's got 4 cores on it. Okay, this actually has the full functionality of 4 separate physical processors on one die right here. So that's why I don't need to have 4 sockets, because I've got all that same power in this one, and it's going to use less electricity, and it's going to run cooler than 4 separate physical processors. Also notice that I think it has it on there. There it is. It says right here it's got 8 megabytes for its cache. So that's actually a really large cache. And like I said before, a lot of the caches nowadays are also getting much larger as well. But anyway, those multi-core processors, it can be started off with dual core, and then AMD has a triple core. Then there's also quad core, and who knows where that's all going to go in the future. One thing to think about with multi-core processors is that you get the advantage there of being able to use multi-threaded apps that can take advantage of multi-core. So for example, an older application might only be able to use a single processor because that's all it's been written to understand is a single processor. Whereas a lot of the newer applications may be able to take advantage of the fact that there are 4 processors and send threads to each one of those processors on the core, on the multi-core processor, and be able to take advantage of each one of them to get a performance increase. In this nugget, we took a look at the central processing unit, or the processor. This was part 1, where we started off with just a conceptual description of the CPU, so you could see things such as the front side bus, the back side bus, the registers, the core arithmetic logic units. You've got a description of what hyperthreading was, all these different kinds of things, which were many of the characteristics that we discussed. And we also discussed additional things such as the cache levels and the things such as to some degree, overclocking, although we'll discuss that some more in the next nugget. Well, I hope this has been informative for you, and I'd like to thank you for viewing.